All right, so now let's think about all the terms that are involved here. And I'll remind you that in an expansion, the system does work on the surroundings, so we want W to be negative. Remember, the gases are pushing against the atmosphere, and we want W to be negative for that transformation so that our sign convention for delta E makes sense. Now, we can first calculate the magnitude of the work done. And I'll remind you that work is force pushed over a certain distance. So you work against a force over a certain distance. So if we define the magnitude of the work to be the force times the distance, first of all, we can rearrange the expression for P external. Remember, it was that P external is equal to the force over area. We can now substitute for the force is the external pressure times the area of the cylinder. And go back and look at the algebra, and you'll see that this is exactly that. And how far did we move that cylinder? We move the cylinder delta H, the change in height, which is the final position of the piston minus the initial position of the piston. Now, this expression here, where F was equal to Px times A, let's rearrange it and group the A, the cross-sectional area, with the change in height. And we've already said that the cross-sectional area times the change in height, that's the change in volume. So we now have that the work done is actually the external pressure times the change in volume. And this is why we call it PV work, right? It actually is equal to the external pressure times the change in volume for the system. But now recognize that this quantity is going to be positive. We have that the external pressure is positive, it's always positive, and that the change in volume is positive because delta H was positive for this particular process. But we want W, the work done, to be a negative quantity. And so we have to define the actual work. Remember, this was just the magnitude of the work done. What we're going to do is we're going to define the work done to be the negative of the product of the external pressure and the change in volume. So now we have an expression that obeys our sign convention for the change in energy. It says that the work done is equal to minus the external pressure times the change in volume. So how do we use this expression? Imagine this problem. Calculate the work done when a gas expands from 1 liter to 2 liters against a constant external pressure of 1 atmosphere. Why would the gas want to do this? Well, if the gas pressure originally is more than 1 atmosphere, then the gas is going to want to expand against the external pressure because the pressure on the inside is larger than the pressure on the outside. And in order to get the units to work out, remember the units of energy are joules, but the units of volume are liters and the units of pressure are atmospheres. And so we need a conversion factor that gets us from liter atmospheres to joules, and that conversion factor is 1 liter atmosphere is equal to 101.325 joules. Now, using our equation for work is equal to minus the external pressure times the change in volume. That's the external pressure is 1 atmosphere. The change in volume is 2 liters minus 1 liter, or 1 liter. And so the work done is minus 1.00 liter atmospheres. And then using our conversion factor and correcting for the number of significant figures, the work done is minus 101 joules. So we can now relate work done, particularly PV work, which is what we're going to be interested in, to the change in internal energy of the system. It says that the internal energy of the system, if there's no heat transferred, so in other words, if Q is 0, what it says is our internal energy has also changed by an amount of minus 101 joules, so that the final internal energy is actually lower than the initial internal energy. And where did that energy go? Well, it went into the surroundings, right? Because the change in energy of the universe is, for the universe is 0, so energy is conserved. When this system does this expansion, what happens is it pushes against the atmosphere, the energy of the system goes down, the energy of the surroundings goes up by exactly the same amount.